All right, hey everyone. My name is Shri Arlagana, and today or this week rather, the topic is going to be about mass spectroscopy. So last week we learned about IR, and we found out that IR is useful for finding out functional groups within a certain structure. Now mass spec offers a different puzzle piece and tools that you can work with to help find your overall structure. It gives a unique tools that are different from IR. So let's get started with some basics. Um, so first off, the first thing you should know is M plus. M plus is the molecular weight. Next, we have M over Z, and this is the mass to charge ratio. So on your graph, we have three different graphs. We have an IR graph, we have a mass spec graph, and we have an NMR graph, or CNMR, or HNMR. For mass spec graph, the higher the bar or the peak, the more abundant the fragment is. And more abundant could also mean most stable. Okay. And then carbocation only fragment. So the carbocation is the only fragment that can detect on mass spec. So as a result, that's why we are, cleaving at certain bonds. So when we cleave certain bonds, we are left with carbons who are losing that electrons due to the cleaving. And when it loses that electron, we form a carbocation. And those carbocation fragments can be detected on the mass spec graph that we create. Okay, so the more stable the fragment is, the more likely they are to form and appear on the graph. Okay, and just a reminder, the carbocation stability trend is tertiary, secondary, primary, and resonance is most stable. Okay, so if we have a secondary resonance compared to a tertiary, obviously the secondary resonance is going to be more stable. Same goes with primary resonance versus tertiary. Okay. All right. So I will give you some examples on mass spec problems and how to solve it. So first we have this structure. Okay, so it's a simple carbon 5 H12, I believe. Yeah, 3, 4, 7, 9, 12. Yeah, C5H12. So it's an alkane. So alkanes are the easiest to cleave because they have, it's just a single like methyl groups or like CH2 groups. So it's not too bad. Okay, and just as a reminder, you want to denote it as, or rather the problem will denote it as with the brackets along with the charge, and by charge I mean carbocation, and then your radical. Okay, the reason why we have a carbocation here and a radical here, because when we cleave, the radical is essentially Let me write this down. Radical is essentially an electron. Okay. So when one side gets cleaved, the remaining structure gets the carbocation, and the fragment will get the radical. Okay. And we'll talk about ranking, mass spec, fragments later on, but let's learn about cleaving first. Okay. So yeah, once again, we form both carbocation and a radical. The radical is the fragment that's left that we cleaved off, and the carbocation is what is remaining that we didn't cleave off. Okay, and to finish out, they might give you mz equals 72. Okay. So once again, just as a reminder, mass to charge ratio. So 72 is the m, that's your mass, and z is your charge, and charge is +1. Okay. So mz in essence gives you the molecular weight as well. Okay. Now let's say I wanted to have fragments that give me an mz equals to 43, as well as mz that equals 57. Okay. So the first step is, and I'll give you kind of steps right here. The first step is to identify m plus or m plus over z to get total weight. Okay. And these aren't like strict rules that you have to follow. This is just what I believe you have to do. The second step would be to find the number, or rather, okay, so subtract the fragment mass from total mass. Okay, and once you do that, you will get, rather, you're not, they won't give you the fragment mass, but, okay, well, yeah, they're asking for the fragment. So you subtract 72 or 43 from 72, and that should give you 29. So 72 minus 43 equals 29, and 29 should signal a special structure. And there's tips and tricks where you can memorize those certain numbers to save on time, as well as recognize these patterns. Okay. So we have to find a structure that adds up to 29 mass. Okay. And this is what we're working with. We only have carbons and hydrogens, no heteroatoms, and heteroatoms mean any atom not carbon or hydrogen. Okay. So that means like nitrogen, oxygen, any of the halogens. Okay. So we have to find a carbon-hydrogen formula that adds up to 29. Okay. Now one methyl group. Let me see where I want to write this. Okay. So one methyl group equals 15, because carbon is 3, and carbon is 12, and hydrogen adds up to 3 each, or 1 each. So someone asked a question, did you already cover proton, NMR, and IR? No. So last week I covered IR. This week I'm covering mass spec. Next week I will cover NMR and probably the following week after that, because NMR will probably take 2 weeks, but depending on when your exam is. But next week for sure I'll cover NMR. But this week is mass spec, and if there's time I can review IR or NMR if there's any questions. Okay, so once again, methyl is 15, and continuing on from that, whenever you add a additional CH2, making it ethyl, you have to add plus 14, okay, because you are adding 1 carbon and 2 hydrogens. So plus 14 to 15 gives you 29. Continuing that, methyl, ethyl, propyl is next. CH2, CH2, 29 plus 14 gives you 43. And then if we want to go one more, which we should, so methyl, ethyl, propyl, and then lastly butyl gives us 57, okay? These numbers I would highly encourage you memorize. It will make your life easier. And I would also know what each structure looks like. Okay, so I'll draw each structure. So methyl is just a carbon. Ethyl, it looks like a line. Propyl looks like a V. And then butyl is that. Okay? So back to our problem. We have a total mass of 72. I subtracted 43. So I need a fragment with weight of 29. Or I have to cut 29, and 29, according to this little key, is a ethyl. So I have to cut a CH3, a methyl, and then a CH2, okay? Now there's multiple ways I can cut. I can cut this way. I can cut right here. I can cut right here. I can cut right here, okay? So I have 4 different ways. And the reason why, just a reminder, you can only cut through a bond. You can't cut through an atom. And especially if there's a fork like this, you can't cut around it, anything like that. Okay? So 3 of these only cut a single methyl. That's this one, or this dotted line, and this dotted line. And if I cut that, it will only give me 15, which is why we have to go to the last slash, which is 29, okay? And that will be where we cut, but it's asking for the remaining structure. So, okay, so don't get that mixed up, and I'll draw both of them so you guys can understand the difference, okay? So that's what we're left with, and because I cut it right, I cleaved that bond, it gains a positive charge because carbon is no longer, it no longer fills its valence electrons. And then in purple is the fragment, is this ethyl, okay? And it has that radical, okay? All right, any questions? Okay. So next up we have 57, and luckily because we already did all the work here, we just have to use this key, and because we already know it in our heads, we can just apply that. Okay. Now 57 or 72, 57, 72 minus 57 gives us 15. Okay. And let me write that down. 72 minus 57 equals 15. Okay, now 15 means we have to cut exactly one methyl. Okay, and luckily we already went over all the different ways we can cut to get exactly one methyl group out. But we have 3 different options. Okay, and that is why the carbocation and radical come into play, because we have to pick the most stable cleaving. Okay, because most stable means more abundant fragment, which means higher the bar. Okay, so mentally do this in your head. If I cut here, there will be a carbocation at a secondary carbon. If I cut here, there will be a carbocation at a secondary carbon. Okay, and that makes sense because these are symmetrical methyl groups. Regardless of which methyl group you cut, you should get the same result. And then this methyl group, if you cut right here, you get a primary carbocation, okay, which is obviously less stable than cutting it here or here, because this yields in a secondary carbocation, this yields in a primary carbocation, which is why we can choose either or. And I'm going to draw what the fragment looks like. Okay, it should look like that with the carbocation here. And just as another reminder, you can cut either this way or this way. It's the same thing. And then on the opposite side, we cut exactly a methyl group. So we denote it as CH3 radical. Now, usually they just ask for the remaining structure and not the fragment that you cleaved off. Okay, but this is in case they ask you, or you have to understand what's happening on the other side, especially for ranking and understanding how stability works. Okay. All right, so that was alkanes. Okay, now we are going to see how cleaving with alkenes work, which is not too different, but I'll give you guys an example. If there's any questions, feel free to type it in the chat and I will answer it as I see it. So next we have the same structure, except at the end we have a double bond instead of a single bond. And as with any mass spec problem, this will be the format. You should see the original structure. And then this time, the MZ is going to be, equal 70, because placing a double bond negates 2 hydrogens, okay? Because we eliminated both of them, okay? Now my fragments are 55, and actually, yeah, just 55. All right, so, of course, we are going to do the math again. 70 minus 55 equals 15. Okay, yeah, that it works to our favor because, as we already know, 15 equals a methyl group, and this time I only have 2 options, and really it's only one option because either way it's the same thing. So I can only cut right here, or I can cut right here. Okay, And for those of you who are watching either live or a recording of this, make sure you're practicing as I'm teaching instead of just watching it, which is fine if it's your first time. But in the future, this is the best way to, try attempt before I show the answer. Okay. So we get something that looks like this. Maybe I shouldn't draw the circle around the charge. Okay. And then the fragment, it doesn't really matter. It's just a methyl group. But the thing is, we have a charge and we have a double bond. Okay. So what can we do with a charge and a double bond? We can resonate. Okay. And we want to resonate and we should resonate because we can turn this structure into a more stable structure. Okay. Hopefully you guys understood how I resonated that. I just moved it over and this is what we get. And if you, one thing I forgot to mention is you should always double check your work to see if it adds up to 57. So let's practice that with this structure. And I will actually zoom in so you guys can see it better. Okay. So I have 4 carbons, 1, 2, 3, 4. So 4 times 12 is 48. I have methyl groups on the side, so that's 3 here, 3 here. So 6 plus 48, that's 54. And then actually I don't have 3 right here because I have a carbocation. I have 2 hydrogens and 3 hydrogens here. Okay, so that's 5 plus 58 is 5 plus 48 is 53, and then I have a hydrogen here and a hydrogen here, okay, which adds up to 55. Okay, so as you see that I had some difficulty counting, so just don't get confused. Make sure you double check your work if something is not right. That means you cleaved it wrong or you just miscounted something. Okay. So let's say we have another structure, and instead of the double bond being there, we have it right here. Okay. And as you know, the mass spec is still 70, and I still want a MZ of 55. So I'll write that down. Okay, I don't need to do the math again because I already know it's going to be 15. So let's draw our potential lines. We could cleave right here, or we could cleave right here. Okay, this time we actually have 2 options. Last time we had 2 options too, but really it was just 1 because they were not unique. Okay. This time we have a carbocation placed right here and a carbocation placed right here. Okay. Now, carbocation placed right here would be a primary, but carbocation placed right here would be secondary. But if you remember from OChem 1, Unit 2, placing a carbocation right here on top of a double bond, we call that something that starts with a V. Right, it's vanillic. Perfect. Okay, so that is why this is not the ideal cleavage. We are going to cleave right here. Okay, so what that should look like looks like that with the carbocation right here. Okay, And we don't really need to resonate this because either way you resonate it, the carbocation will be placed, or not the carbocation, the double bond rather, will be placed in the middle, or it's the same thing as what I'm trying to say. Also, one thing I realized is you might be wondering why we resonated it, because the carbocation goes from a secondary to a primary, and that might look unstable. But I think the point you should understand is that there is resonance, and you should view this as a pair. The resonance is not too important, honestly. I would just focus on understanding that there could be resonance and the positions of the carbocation and the double bond. Okay? All right, so we have two kind of special cases. Actually, we have two special cases. And then I'll talk about heteroatoms. Okay? So I am actually going to have to erase this page to make room. So if anyone wants to take a screenshot right now, this will be the time, or take a picture, whatever you want, before I delete it. Of course, in a recording, you'll still have access to it. Okay? So first, we are going to talk about something that's called, we're going to talk about alcohols in our structures. And specifically, we're going to talk about one, dehydration, which is loss of H2O. Okay. And some characteristics of this type. You form, when you get rid of the alcohol, you are also getting rid of a hydrogen, to get your H2O. And usually when that happens, we eliminate. And when we eliminate, we are forming a double bond. Okay, so formed an alkene. And if you see a peak that is 18 less than its M plus value, it's because of dehydration. Okay? So let me give you an example of what that looks like. Okay, so we have this example. Don't forget to put your brackets, plus radical, and let's say the mass spec, or MZ, is 74. Okay, and I'm trying to get to a mass spec that is B6. Now when we do the math, 74 minus 56 equals 18, right? And 18 isn't one of those numbers I showed you on the previous page. It's not a perfect methyl group. It's too little for ethyl. So it cannot be just carbons and hydrogens. Well, it can be, but actually, no, it can't. So the only way we can get this combination is if we introduce another atom. In this case, it's going to be the alcohol. So as you know, oxygen is 16, and hydrogen is 1. And when we cleave it, remember we're also cleaving this one of these hydrogens, or electrons rather. And so that provides us with the third or second hydrogen. So that should look like this. And this is not the final, what it looks like. So, and you'll understand what I mean. Okay, so we have that, and we have a radical, or rather, not a radical, we have a carbocation right here, okay? And if you notice, this should be a methyl group, but because of the carbocation, it has 2 hydrogens, and this also has 2 hydrogens, okay? And yeah, let me draw that. 1, 2, 1, 2, okay? So instead, we are going to we're going to create a double bond between those 2. And now it only has 1, okay? And that's where the extra, the extra hydrogen doesn't come from here. It comes from when we turn it into a double bond. That's how we cleave it. Let me see. Yeah, okay. So just as a reminder, the final answer you should get looks like this. So once again, every time you get a mass spec that is 18, understand that water is involved, and anytime water is involved, your structure should have a alkene at the end. So wherever it got cleaved off and there's a plus charge, form a double bond with the carbon that's bonded to it and get rid of the plus charge, okay? And the plus charge is not needed in your final answer, okay? And there's different notations of how professors like to use this, so make sure you understand how professors note this, and I mean like the plus radical charge, because that part is also confusing to me. Okay, so the second part is alpha cleavage. And what alpha cleavage means, it basically cleaves off the carbon with the oxygen bonded to it that is connecting to the alpha carbon, okay? And fragmented carbocation will have to resonate with the oxygen, okay? And I'll give you an example to make sense of what I just said. So same thing, except this time the alcohol is right here, okay? Wherever the alcohol is, in relation to that, the alpha carbon is right there, and the beta carbon is right here, okay? Now, of course, this is also an alpha carbon, but we're going to pay attention to the right one, okay? So let's say I have a mass spec of 74, or MZ value of 74, and I'm trying to get to 45. Okay, and then if we do our math again, 74 equals, or 74 minus 45 gives you 29. And 29, as you know, is ethyl. So we have to cleave both beta and alpha carbon. And the reason why we can't cut this alpha carbon is because there's no, it won't match up with our fragment. Okay, that's why we have to cleave right here. And this is when we cleave the carbon that contains the alcohol and the carbon that is directly 1 carbon away, this is what that is what alpha cleavage means. Okay, so it's nothing special. It's just named alpha because there is a unique special group that you can see. Okay, so once again, we're cleaving right here, and what you're left with is something that looks like this. And again, this is the most stable form because using the lone pairs from oxygen, this positive charge can form a double bond and place the positive charge on oxygen, and that makes it more stable. Okay, so in reality, there is resonance here, and what that looks like is this. With the positive charge on oxygen. Okay, yeah, someone is asking, can you explain how to know where to cleave it again? Yes. So this is the total mass, 74, and this is the fragment I'm trying to get. So 74 minus 45 gives me 29. And from our previous page, 29 is ethyl. So one methyl group and one CH2 group. Okay. So because of that, this is the only way, the only combination, and the way the structure is formed, this is the only possible location to cut. Because if we cut right here, we are only cutting the methyl group. If we cut only here, we are only cutting the alcohol, which is, we're not, it's not a dehydration. We're not trying to get rid of only 18. We're trying to get rid of 29. And we can't, again, like I said, we can't cut like around the circle or around the bond, anything like that. Does that clarify it? Your question? Okay, perfect. So yeah, just so understand that there's resonance and it's very stable to have a charge underneath the alcohol because of resonance. Okay. Now let's say I have this structure. So the same structure as the one above, but we're still trying to, the mass spec this time is going to be m over z equals 74. And this time, let's say we have m over z equals 31. Okay. So when we do our math, m over z, or sorry, 74 minus 31, that should give you 57. Yeah. 57. Wait. No. One sec. 74 minus 31. Sorry, that gives you 43. I added an extra 14. Okay. So, which is fine. As long as we get 29, 43, or 57, we're happy. Okay. So, 43 means a propyl. That means we are cutting 3 carbons and some hydrogens. And the only possible way is cleaving it here. Okay? And then also to denote our structure, this is where the alpha carbon is. This is where the beta carbon is. And so 1 carbon away is going to be alpha. 2 carbons away is going to be beta. And then 3 carbons away is going to be gamma. Okay? Which is like your Y. Okay? Again, you don't count this carbon because you're counting one carbon away from the carbon bonded to your special group. Okay, so one carbon away from this carbon. So don't make the mistake of making this your alpha, this your beta, and this your gamma. Okay, and this is really, you don't have to do anything special with alpha, beta, gamma. It kind of just, if anything, it just confirms where you're cleaving in relation to your alcohol to get the desired product. Okay, and the problems that are given to you should match up. And if something doesn't match up, you either you messed up somewhere. Okay, so the final product should just look like this. Just one carbon. Okay, and again, because all of these can resonate, so it can form a double bond like this, and then oxygen would have plus charge. Okay, and just to remind you guys, the reason why it can resonate is because the lone pairs can act as a double bond for resonance and provide those electrons that way. And because the oxygen is losing a lone pair, it gains a positive charge. Okay? All right. So we are almost done. But I will have to erase again, so make sure you have everything down, screenshot it, whatever you need to do. And I will erase now. Okay. So we also have ketones and aldehydes. And first one is going to be, again, alpha cleavages. Okay. So our first example, so this time we are dealing with carbonyls. And our first example looks like this. Okay. All right. And because of this, like I said, your alpha carbon is going to be one carbon away from your special group. So these are your alpha carbons. This is your beta. This is your gamma. And gamma can also look like this upside down. It looks like a bird or a bi. Right. So there's no real lesson here. So when you do cleave right here or right here, so going from the right side, you should get something that looks like this. Okay, and again, oxygen has resonance. So even though it already has a double bond, you can make that into a triple bond. And I know that looks really weird. Hopefully you won't have to do something like this, but it could look like that. Okay. Now it could also look like this. Just showing the other side. Resonate it, and then you have the same thing, except with now a triple bond on oxygen with a positive charge. Okay. So nothing really special. The reason why alpha cleavages are talked about is because you want to cleave right underneath the oxygen because it provides stability, it provides the resonance it needs to make that happen. Okay. That's why if you only need to cleave a methyl group, you choose this one and not this one, okay? So really make sure you understand why when we only subtract 15, we're not subtracting right here, we're not cleaving right here, we're cleaving right here, okay, because of the stability. Okay, hopefully that made sense. But yeah, so the last example rather, we're going to talk about is something called McLafferty rearrangement. Hopefully you guys have heard of this term in lecture. If not, you might get to it. So McLafferty rearrangement must have a gamma carbon. So what gamma carbon means is 3 carbons from carbonyl. Okay. So, and this also happens so with McLafferty rearrangement, we end up with a extra +1 mass, okay? And I'll tell you where that +1 is coming from, or rather I'll show you, okay? So we're gonna use the same example, or almost the same example. Sorry, let me redraw that. Let me draw a little bit bigger. So we have this structure. And let me label alpha, beta, gamma. And I'll just type it out this time, beta, and then gamma, as you know, looks like a Y. Okay. And we are going to rearrange it so that the gamma carbon is right next to the oxygen in the carbonyl so that the oxygen can abstract the hydrogens on this methyl group. Okay. I know that sounds a little bit weird. It may look weird, but this is the right way it happens. Okay. And on that carbon is a hydrogen that is forming a connection okay. Oh no. Okay. Let me do that again. Okay. It's forming a connection with the lone pair. The oxygen lone pair is abstracting this hydrogen, and we're still gonna, the alpha, beta, gamma are right here. Alpha, beta, gamma. And we're still going to cleave at the alpha carbon because it's still the most stable. Okay, and what we end up with is and that extra alcohol. Wait, 1, 2, 3, 1, 2. Yeah, so it could look something like this, and I'm sorry, this is a little confusing to me as well. But so it could look something like that, I think, but you also see it as in an enol formation rather than the keto formation. Okay. Because what's happening is this cleaves right there. This goes right here. And this bond forms a double bond to the alpha and the carbonyl. Okay? So that might not look too... Sorry, this should be pointing somewhere else. Okay? So that might be a little bit confusing, but to summarize, make sure you understand that it rearranges like this, and that oxygen gains an extra proton, and then there is sometimes the enol formation, and basically the end result is you get a +1 to the mass. Okay, so when we're cleaving, let's say you cleave alpha right here, and you get like 56, but you really need 57. Those are just made up numbers, by the way. If you get one short of the mass you need, that means you have to do a McLafferty rearrangement. But make sure you have enough carbons to do that in the first place. You have to have 3 carbons away from the carbonyl, or in other words, you have to have a gamma carbon. Okay? So lastly, I want to talk about the heteroatoms, and then we'll be done. That is my attempt out of line. Okay, so we're going to be talking about bromine, chlorine, iodine, nitrogen. Actually, let me move everything down. Yeah, iodine should be right here. Nitrogen. And then last we have sulfur. Okay. So these are called heteroatoms. These are atoms that are placed onto your structure. And when they're placed onto your structure, they have unique mass spec characteristics. Okay. Just like in IR, when a alcohol has that broad peak, or like a carboxylic acid has that even larger peak, broad peak that looks like an upside down mountain, stuff like that. You have that in mass spec also. Okay. And usually you have a M plus value and a M+2 value, okay, which just means 2 more mass on the graph. So it should be literally right next to it, okay? So I'm going to show what it should look like for each of these. So for bromine, if the M plus value looks like that, and let me actually put it much closer, and maybe zoom in. So M plus and M+2. If your M plus looks like that, your M+2 should be roughly the same. Okay, it's not identical, so let me make this a little bit longer, but it's roughly the same. Now for chlorine, it's going to be 1/3 the size. So if M plus looks like that, M+2 is going to be this tall. Okay, so that's roughly 1/3. Sulfur is going to be, it's going to have a 90 to a 10% ratio. If your M plus looks like that, your M+2 will look something like that. Nitrogen will not have a unique M plus character, but whatever it is, it's going to have a odd number. Okay. So any odd number as your m plus, and your fragments are going to be even number. Okay. So any odd m plus is automatically contains a nitrogen. And then for iodine, it's going to be also something specific. It's going to be odd, but it's going to have m. If your m plus value equals exactly 127, that means you have an iodine in your structure. Okay. So any odd number except for 127 obviously is going to be nitrogen. If you have a 1 to 9 ratio, it's going to be sulfur. If you have a 1 to 3 ratio, it's going to be chlorine. If you have like a 1 to 1 ratio, it's going to be bromine. Okay? So those are the heteroatoms you should be aware of. Patterns you should look out for on your graph. So let me write this down. So like 1 to 1, 1 to 3, 9, any odd number, and 127. Okay? All right. So those are all the heteroatoms, and that should complete the lesson on mass spec. And then giving you different examples of how to cleave it and different ways you can cleave it, and like the notation of it and how to find, how to subtract, and how to get the results you want, the difference between carbocation and radicals, what m plus means, what m over z means, the abundances of the fragments on the graph. Obviously, the more problems you do, the better you'll get at it. Mass spec, I would say, is the less important of the three, or the least important of the three. NMR is the most important, and then IR, but that's just my own personal opinion. Each semester it changes based on the amount of questions they put for each spectroscopy method. But yeah, if there's any questions, let me know. Or if you want to attend next week's lesson and bring those questions there, we'll talk about it. But other than that, next week we'll talk about NMR, and I'll continue on from there. All right, if there's no questions, I'll end it here. I'll see you guys next week.